Okay, so I have shared the first lecture content on Blackboard. It's not slides. Okay, so for today's class we'll try to go through these notes together, and I'll try to use this new gadget that I'm trying to use for today. It may fail, but we'll see. So I hope everybody has access to these notes or a PDF of the notes from Blackboard. Okay. Okay, so today's topic is going to be supervised learning, and as you might have seen in other data science related courses, the first class inevitably talks about the impact of data science on various industries and the significance of learning some techniques or some understanding some techniques and tools to harness this data to whatever purpose you want to use it for. And so here I've listed on the first page some application areas. I mentioned sports analytics, retail and pricing, which is a very significant impactful area for businesses, advertising and personalization. So the biggest companies in terms of market share or revenue are like Facebook and Google. The biggest workhorse is the advertising thread. So a lot of statistical models are built by them to understand and effectively deliver ads, I guess. There's also impact of data on social networks. You want to harness the data to understand what's happening on networks, online communities like Reddit. You have MOOCs and even in education. For example, on Blackboard tries to track who accessed what at every point of time. For example, I don't know if the instructor can know, but Blackboard definitely knows which student has accessed the lecture. For example, the lecture PDF today at what times. For example, some of you might not have accessed it. Somebody's logging that. For some use, they're trying to improve their UI, their offering, whatever that is. I have worked in my own research. I've worked on applied problems related to transportation systems. For example, think of ride sharing. Okay. In ride sharing, you can bring in personalization of the whole service. It's a shared service system. You can bring in personalization by trying to learn some characteristics of the ride sharing participants. So, for example, if you don't want to ride share with people who talk on the phone during the ride share, then maybe you give a bad feedback after the ride share, and using that feedback, learning system or somebody, a data analyst, can figure out that maybe they should change the strategy in which they're putting people together. Okay. This field of automatic speech recognition with Siri and Cortana and so on. I mean, it's been there for 50 years. We will see how they ramp up. There's a lot of applications in computer vision, which is where this whole interest in deep learning restarted. If you want to know a little bit about deep learning, you can take the 576 course. There's also applications in fraud detection and finance, which are really major areas in these industries. Fraud detection in healthcare and finance help these companies mitigate the risks and try to weed out issues in their processes. There's also a big impact of using data to improve health outcomes. Although there's a lot of regulation and a lot of other non-technical things which may be modulating the impact of data science there, but it surely is going to influence significantly this area. So let me go into one application which is on the notes, which may be interesting to you and hopefully gives you a little bit of a one level of a deeper view in one such application of statistical modeling. Okay, and this is an application in sports analytics. Sorry, I'm not using the board right now because there is no nothing technical here. But so this is the this is a particular problem in sports analytics, which I worked on several years ago, which is as follows. So how many of you follow some form of car racing? Okay. Do you know any sport, any particular sport? So name one particular sport in car racing. Like there's some. What is it? NASCAR. Yeah. What are the, there are some other ones as well. Yeah, Formula 1, right? Yeah. So there are a couple of different, I guess, organizations which have these races, which there are like a sequence of races per year. There's a lot of investment into the hardware, into the cars, and training the drivers, and so on. It's not, I guess, it's not a sport as big as probably NFL and NBA and so on. It's an interesting sport. So the particular statistical modeling question there was to build a decision support tool. So what is a decision support tool? So there are people, like in the sport, there's teams. So in the car racing sport, there are going to be, let's say there are 10 racers, then there are 10 teams, and each team wants to make the best decisions during the race, so as to get their driver to the top of the podium. Okay. So they want a decision support tool, which means that they're still going to take decisions at the end of the day, but they want information condensed in a form so that they can take better decisions. Okay. And as you will see in many business applications, the end goal of statistical modeling, although in the books, the end goal of statistical modeling would be to improve whatever other performances there are. They have to ultimately translate to improve quality of decisions. Okay. So here in this particular sport, the decisions for the team are going to be how to take pit stops, when to take pit stops, what to do in the pit stops. Okay, these are the decisions that they want to take. A pit stop is nothing but a stop that a car racer takes during the race to refuel or to change tires or to kind of refresh the car so that the car can do better in the next set of laps or something like that. Okay. So the precise question that the team wants answered through statistical modeling is, can you use live race measurements seen so far for everybody, not just their own driver, but whatever measurements you can make with all the racers in the game up to some point, maybe after 100 laps, can you use all the data to forecast some numbers into the future, and use those numbers to determine this the question that I really want to answer, which is when to take a pit stop, what to do in a pit stop, so that's what I want to do. Okay. And so the extreme, the zero dollar question that you need to ask is there even predictability in this code? Okay. So is there anything predictable? What do you guys think? Yes. Why do you think there is predictability? Yeah, the tires wear out. Yes. Yeah, the fuel is consumed, so the car is lighter, and so the characteristics on the road are different. Yeah, the weather also plays an important role. So when I asked this question, I was thinking of, is there anything that will hamper predictability in this observation of measurements? So accidents. Okay.
Changes in human behavior.
Yeah. So that's true. There are other people in the system. So this is a game. So other people are also strategizing, and they may change their strategies as a function of time. I mean, as the race evolves. So it's not clear that you can predict. It's like if you can predict what they're going to do, what everybody else is going to do, and how the weather is going to play out, how the tires are going to play out, maybe you'll be able to predict the future. But these are the two competing forces. Like you need to know what the other guys are doing potentially to do something meaningful. If all the other drivers, whatever they do has no influence on your outcome, like how your car performs, then it's fine. You don't need to know. You don't need to capture the effect of other drivers. Okay. So that's why I asked this question: is there predictable in the system? Okay, so let's assume there is predictability in the system. then so let's formulate, let's say there is predictability in the system. Let's get some data. So what is the data here? The data is going to be just lap times and rank positions of different drivers so far, for at least all the drivers in the race. And maybe for your own car, you may know how much fuel you have. You may know the tire characteristics, for example. You may have a model for that. Because you can't measure in real time, at least in this course you can't have measurements or sensors which will exactly tell what's the status of the car for some restriction. So you have this data, so simple data, or maybe you can also have data which is how much time did it take a pit stop, for example, if you had to change 2 of the tires in your car, or how much time did it take to change 4 of the tires in your car. Of course, taking 4 tires will take more time. So in the note, I have some plots which I guess I can recreate. So the plots are as follows. So let's say this. So the plots are as follows. Like the first plot I plotted was just the histogram of times, okay, of pit times, okay. So there I observed a histogram. Histogram is just every pit time you see, you just bin it into some time interval and just look at the frequency of the number of observations that had that pit time, okay. So I see I guess something like this. And then there is some histogram like this, and then there is something like this. Okay, so there seem to be 3 bins in the notes. So okay, so the 3 bins are because I guess most people here probably took 2 tires. And all the drivers over here probably took 4 tires. Okay. And this is actually because of what? Huh? Yes. Yeah, they have to take a penalty, which is they just have to go through the pit lanes. They don't want to stop at the team to refresh anything, but they were penalized for doing something incorrect. So you have these observations as well. If you look at the so I have another plot which is to the right of that, which is looking at as a function of rank. It's just plotting a lap time. Lap time is just number of seconds that a car takes. So the lower the rank, the lower the lap time, and higher the rank, for example, the higher the lap time. So you have some sort of linear relationship between. So this is at a given lap. Tell me at this rank what would be the lap time of a person. So there seems to be some linear relationship. But is that useful to predict the future? Well, we took a snapshot at any given lap, so there is no temporal aspect here. So let's look at temporal aspect. So here's the third graph, which is bottom left, is showing the so it seems like it's showing a bunch of lap times actually as a function of lap itself. So this is the time, and it's showing time as a function of lap number itself. So in this particular example, I think there are 500 laps. Okay. So there is a bunch of time instances that you can see here. It's something like this. Okay. So I'm just trying. So these are actually just observations, like. Okay. So why do you think there are discontinuities here? This is just the observed lap times of a driver as a function of a lap. Any guesses of why do you think there is discontinuity? Yes, pit stops, and you can see that after the pit stop, the driver has better lap times, right? And it's kind of becoming worse, and then therefore, it makes the decision even more important. At what time should you go back in? Because the issue is if you go back in, you lose time. Other people would have overtaken you, maybe even lapped you, which means that you are 1 lap down or something like that. So there is this trade-off that you go in, you want to have a better car, but if you go in, you have a loss in rank. Okay. So these are some. there is some exploratory data. Given the data, you can kind of plot these things and maybe understand what the domain is about. And the last plot is showing a particular dependency between two different derived variables. So it's just, I'm not going to draw this particular last plot. It's just some correlation plot. Okay. So you can do all this initial analysis of your data. Okay. And the end goal is to somehow predict some reasonable statistic of the future, such that people can make decisions out of that. Okay. Take decisions out of that. And in this particular application, with the help of some experts in the domain, decided to take the change in rank, okay, rank positions in the laps following the pit stop, given what happened in the pit stop and what happened before the pit stop. So the thing that I wanted to predict was what would be the change in rank if you took a pit stop, you did something during the pit stop, and what happened during the race. Okay, some relationship like that is what I wanted to capture. Somehow predict something like that. And I also in the notes have plotted pretty much what I did back then, which is I tried all sorts of popular predictive modeling methods. I don't know if you have this plot in front of you. It's basically, let's look at just the top plot. It's just some number, RMSE. Okay, we're going to discuss what exactly RMSE is pretty soon. Some performance of a predictive model. Okay. So on the x-axis, I'm just taking model 1, model 2, model 3, model 4. Okay. Let's say there are 4 models. I think there are 4 models and a couple of baselines. So anyway, the few models. In this case, the keywords are ridge regression, support vector regression, lasso, and so on. But we'll get to what these are anyway in the course. So. And I've also broken the data into 2 sets, which means that I somehow did some sort of clustering or partitioning of this data, because I thought, okay, one set of the data may have different characteristics than the other set of the data. And then for each set, I fit these predictive models which will predict the change in rank, and they have some numbers, okay, some RMSE values, something. Okay, so you can do this if you did not take this class. Okay, you can import a regression package or a support vector regression package, or packages which include these methods, and you can plot those and show this to your manager, and maybe it will be deployed. Okay, but in this course, we're going to try to delve deeper into why some of these methods work, why some of these methods don't work. And what assumptions these methods are making to make a prediction of the future. Okay, so that's just a motivating example of one application which involves going from data, measurements of laps and ranks, all the way to decisions, which will be useful for the team to actually make win the race. Any questions so far before we actually get into some details?
What are the examples? Is the speed or time taken for an
x-axis is different models. So I didn't plot. So each model will have some inputs and outputs. So we're going to discuss what exactly a model means and what are the inputs and what are the outputs right now. But all I'm saying is, in this application, I had some data. I looked up, I plotted histograms, I plotted some correlation plots or whatever, and from that given the correlation plots, I thought some of these can be. And if you've done statistics, some of these can be independent variables, and then the dependent variable was change in rank in the next after the pit stop. And so I just use some popular packages, popular techniques to fit a model. Okay. Yeah. I will get into the details of what these models mean pretty soon. So we'll start from scratch. Okay. So. The first topic is going to be, we're going to start with trying to get some jargon into this, because we want to describe what we're doing in a little bit more formal manner, okay, which is what I call the language for statistical modeling. Okay. By the way, there's a book for this course that we're going to follow. It's called Elements of Statistical Learning, second edition. It's available from the author's web page. It's also linked on the syllabus page. So please have a copy of that so that you can follow the book and the notes more thoroughly. Okay. So let's start with the first topic. We're going to build some vocabulary now. So I used some vague words in the previous description of the application. So now I'm going to kind of tell you what those words mean. So let's say there are some inputs, and they are somehow allowing me to tell something about some other quantity of interest, which is change in rank. So those are the outputs, right? I also use the word variable. Okay. So a variable just means something which can take different values. Okay. For that, we just using the placeholder symbol, right? So these variables can either be physical measurements, which is what was the case in the car racing example, or they can also be other things, like you can if you're you have a marketing assignment that you need to do some market research, you can conduct surveys. So these measurements can be just need not be using sensors or something like that. Okay. We hypothesize that there is some way to construct kind of say something about the output given the input. Okay. So that's key hypothesis here, and we're going to call this procedure of going from inputs to outputs supervised learning. Okay. There are a few additional ingredients to supervised learning. Okay. A few additional ingredients to supervised learning, but let's think of just in terms of input and outputs for now. So all we're trying to create is something called a function, right? Or a map. A function is also called a map. Okay. And any process or any method that does tries to figure out this function or a map, we're going to call it a learner. Okay. It's just jargon that we want to use. Okay. And in notes I've given some synonyms for this. So for inputs, I'll also call them predictors or independent variables, which you might already be familiar with, or features. Okay. So when somebody says features, they just mean some inputs or some observations or predictors which can predict something. Okay. Outputs are responses or even labels. So let's focus on outputs for a bit. Outputs can be both quantitative, okay, and they can also be qualitative. Okay, so by quantitative I just mean that they take numerical values, and by qualitative I just mean that there could be some semantic symbols that you can assign to the output. For example, the output can be like happy or sad, for example. Maybe that's what you want to predict. Okay, happy and sad are just semantic notions of that you can predict. So that's what I mean by qualitative. And in the quantitative setting, okay, we're going to call the map a regression function. Okay, this map that I was talking about. Yeah, so this map or function that maps inputs to outputs in the quantitative setting, we're going to just call it regression function, okay? Or we can just call it process. So the process is going to be called regression. The general vocabulary is supervised learning, but you have a quantitative output, then you call it regression, and the function itself, you can call it a regression function. Okay. And similarly, on the qualitative side, we can call the process classification, and the thing that you build, the function or the map, it's called a classifier. Okay, so you might have heard of span classifiers or object classifiers or something like that. For example, maybe there's a classifier which can classify a dog versus a cat. Those outputs are not really quantitative, right? They are qualitative, right? There's no measure or value to what a cat means or a dog means intrinsically. Okay. So in the notes I've given a couple of examples actually. So for example, when a learner is doing the task of supervised learning, a learner is doing the task of regression, a learner is going to do the task of classification. So when the learner is learning this function, okay, so let's say they're learning a cat classifier here, then we can specify a representation for this output. So if you're trying to classify, if you're trying to figure out a classifier, which is this function, you want to first specify what is the representation of the output. Of course, it's going to be either cat or no cat, right? But I want to have something, I guess, easier to work with. So I'm going to map the cat to a value 1, okay? And I'm going to map the no cat situation to value 0. So there are two outputs, the two values the output variable could take, cat or no cat. And I'm going to just assign a value 1 to when the cat is present, is essentially equal to 1, and the no cat set, I guess, is equal to 0. I could set something like this, and this could be the output, or I could flip the representation. So that's what we just mean by when you have qualitative outputs, then you can just assign whatever you want. As long as it's convenient for you to figure out the function, which is what you want to do, figure out the classifier. Okay. So another example of a qualitative setting for the outputs is that of, let's say, a very stylized model of autonomous driving. So in autonomous driving, you have these features. So if you remember, features were just inputs, right? Features, inputs, predictors. So all these features were just measurements of various things, like the location of the car on the street, the location of people, location of other cars, other things, like the brightness of the environment and so on. Those would be the measurements of the features. And then all the way to this side, the outputs could be qualitative. For example, could be in the example I've said accelerate, brake, turn left, turn right, or steer left, steer right. So those could be the qualitative outputs. So those are the output descriptions. Now to actually do something about it, you may want to map them to some other representation. For example, you may want to assign a number to each of these potential values that the output can take. Okay. So remember, inputs and outputs typically will be variables. The values that they take, we'll call them realizations. Okay. We'll see as we move forward. So once we've described what inputs and outputs are, we can now describe various statistical modeling instances that you might have already seen in other classes, as well as we're going to just bin them into different things. Okay. So why are we calling this, first of all, why are we calling this statistical modeling? Is because we're going to use the tools and technology of statistics and the notion of probability to understand what exactly are the assumptions being made and what could be the errors, some very formal way of describing what would be the errors if you assume some statistical model about the data, for example. Okay. So few subtopics in statistical mining include pattern mining. For example, if you have a database and you want to figure out patterns in this database, for example, somebody who's getting a very high grade in every course and maybe getting a scholarship, that's a pattern, maybe occurs simultaneously. There's this task of clustering where you have again a database with different maybe student entries and student characteristics, and you could cluster students into like some people are really good at sport and people who are really good at music and so on. So that would be partitioning your data into clusters. Then there's a task of classification and regression that we just discussed. Okay, and there are some other tasks like ranking. So given an input of a bunch of given an input of a bunch of like let's say input is the features of a bunch of students, then you may want to rank them according to aesthetic ability or something like that. And there is this other task of density estimation, which is to fit actually a probabilistic model for what the data is about. So let's say you're measuring the height and weight of every student in the class. Maybe you can fit a Gaussian distribution on that. Okay, that would be just a density estimation problem. Anyway, so just to kind of ground that there are all these different techniques, and some of these techniques you will see in other classes. They can all be considered. They can all be looked at from the statistical modeling point of view. Okay. So just a notation, we're going to use capital X to represent the input variable. Okay, it's not. It can be a scalar or it can be a vector. Tell me if I use some jargon which I've never heard before. I'll just clarify it in real time. So we're going to use X to represent the input variable, and one ingredient that I kind of skipped when I said that this is a task of supervised learning while you're trying to figure out the function or the map between inputs and outputs. That ingredient was data, right? You can't just figure out a function from thin air. You want to figure out the function using some history, which is the data. Okay, so we're gonna have a data set whose ith observation will be represented using the lowercase x with a subscript I. Okay, so for example, how does the data itself look like? It's going to be, let's say for the inputs, it's just going to be x1, x2, xn. Okay, so these are just values that the input variable is taking. Okay, these x's need not be scalars. So for example, x can be three-dimensional vector. Okay, and if it is p-dimensional, all these observations or all these realizations are also p-dimensional, right? All these values that the input variable is taking is also p-dimensional. So we're gonna, let's say we stack them. So okay, another quick thing is that we're gonna assume, let's say if it is a p-dimensional vector, then we're gonna assume that it is a column vector. It's just so that there is no ambiguity between a row vector and a column vector. Column vector just means the numbers are stacked vertically. Okay. And now I'm going to have another representation, which is this matrix X. Okay. It's a boldface X in the notes, but I can't write boldface, so I'm just putting a tag here. It's going to be x1 transpose, which is going to be a row vector. Okay, xn transpose, row vector. So I'm just just flipping the vectors x1 to xn, making them row vectors and just stacking them one after the other. So I get a n times p matrix. Okay, that's my one part of my data. For supervised learning, you need both the features and the labels that you've observed. So this is what observed features would be, a set of observed features. So when I said x is p-dimensional, think of each coordinate as kind of a measurement, right? For example, one coordinate can be the weather currently, one coordinate can be the quality of the tile currently, and so on, right? Some number that you can associate. Maybe weather is not exactly numerical, but maybe you can make it numerical. Okay. So given that, what do you think so given this matrix capital X, lowercase x there, what does the jth column represent? Any idea? Yeah, I think here's some numbers. Yeah.
x1j.
What was the question?
What does the jth column represent in this matrix?
One dimension in your observation is could be any single variable, or you have a variable wrapped in a vector, could be one dimension.
Yeah. So one column is just, as we said, one column is just a sequence of n observations of the same variable, for example weather, or same variable, for example the quality of the tile. Okay. It's just it's kind of, you need to be familiar with, okay, what are rows, what are columns. A row is just the observation, so all the different things that could have happened for that observation, and a column would be, across observations for a given dimension or a given coordinate or a given particular attribute that you're measuring, all the different values of that. Okay. So we introduce this notation. So similarly, let me introduce the notation for y. So I'm going to use capital Y to represent the output variable if it is quantitative, and I'm going to use capital G to represent qualitative variable. Okay. So with just this notation, we'll bring in statistics and probability a little bit later. But with just this notation, we can kind of actually describe what we wanna do in any of these data-related tasks, or a large subset of these data-related tasks, specifically classification, regression. We just wanna figure out something that goes from x to y or g, right? That's what we wanna figure out. And let's say we have some function. I'm going to use f to represent the function, okay, which takes x as input, and output something. Let me call it y hat, because that's specific to that function that I picked. Okay, we just want this y hat to be close. I'm going to use this squiggly equality sign to represent that y hat should be close to y. Okay, so that's what we want to achieve in the supervised learning task. Okay, so one quick question is, let's say G only takes two variables. G takes two variables, so G can take a value 0 or 1. Okay, I mean G is a qualitative output, so let's say it's cat and no cat, and for cat I said 1, and for no cat let's say I said 0. Okay, that means that I've assigned these two integers to this particular qualitative variable that it can potentially take. So can we use Y to proxy G? So why do you think we cannot, or why do you think we can? Any strong reason for?
Because the output is binary, so either it will be 1 or 0.
Yeah.
So if it is going to be 1, then we can convert it to 0. So there are two
Okay.
Still it comes with categorical variable, not the quantitative. So
If you convert it to a number, it's a quantitative.
So I guess even if I assign these two numbers 0 and 1, if I want to use Y for G, maybe I have to think about an order relationship between these two. Right? When I said that when something is a quantitative variable, there's going to be an order relationship. Like if some quantity takes a value 5 and another realization or other value that it takes is 10, there is an order relationship that 5 may be less than 10 or 5 may be greater than 10, whichever direction you want to see. But here there's actually no order relationship. But if we proxy G with a Y, let's say you could do that. I mean, you need to be aware that you may be imposing an order relationship. Sometimes it doesn't matter whether you impose an order relationship or not, but sometimes it may matter in your interpretation. Yeah.
So as you took an example of a cat or no cat for a G, but
Yeah.
in terms of quantitative cat, I will have, as you said, order relationship. But then you said that you may have it here. There may be cases where we cannot, right? The quantitative may represent the attribute of the cat.
Yes.
So
There may not be any order relationship, but you could proxy G with Y, but you need to remember that there is no order relationship. Yeah. In a sense, let's say you had no idea that there was no order relationship. You just replaced G with Y and you carried on your analysis. By luck, you may not run into any issues.
there will be.
Yes. Okay. Okay, so this is just introductory notation. Let's take a break for 10 minutes and then we're going to resume with some couple of specific methods.
Next semester or is it going to be next year?
No, it's going to be next semester as well. Because I'm not logged into Blackboard. Okay, let me do it in a way that is, I need to see my password. Actually, I think this is coming.
Syllabus came and that should also come, right? Like I'm not sure as it was.
Yeah, can you refresh?
Yeah, I did. I was trying to do the entire class, but it's just this.
Oh, okay. One second. Sorry, I'm calling the password.
So just share one extra document after syllabus.
Which is the lecture notes, Okay. So if actually I can see in the student pool, I can see people having access to the both syllabus and
I'm not
lectures.
sure why I'm not getting the syllabus. It's just the syllabus.
Okay, I'm just saying that. Hey, that's able to access the.
Sure, otherwise it just coming syllabus for me. And can just enroll also.
So we go there.
Even the thing is not coming.
Is there something blocked?
I'm getting the syllabus one, right? Just a lecture.
Can you borrow the notes for now, and then after the class you can just fix it.
Okay.
Just take the notes from the time, right after class.
Okay.
To just to the leadership that we so that starting that as well. So we want to say that if I quantitative, I need to have higher values. So if I let's say
Not high values. Quantitative just means that like it was an arbitrary decision to give cat is equal to 1, right? You could have given cat is equal to 1,000. No, you could given any number. It wouldn't have mattered.
it's still a higher regression.
Doesn't matter. For quantitative ones, for quantitative ones there should be orders, right? Like whether the temperature, for example, there is an order 6 degrees is smaller than 28 degrees. But on this side, once you give numbers, for quantitative, you assume you may we just have to keep the order in our mind. You should know that there is no ordering that you may inadvertently impose. Like when you put in numbers, once you put in two numbers, of course, either A is greater than B or B is greater than A, right? But there may not be any such interpretation in your original data. Qualitative means
In the original.
yeah, in the original data. But once you assign numbers, you should not assume that there is a order. Capital X is like variable. These are realizations of the variable. The smaller x represents like the value that the variable takes. If this is scalar, then this is the scalar. If this is a vector, then this is a vector. So I said x is a p-dimensional vector, then this is going to be a p-dimensional vector. It's just numbers that, like, you know, if you program it, then you know that variable can take arbitrary values, right? The values are these guys, and such values that it took. The generic symbol that we're going to use to represent the variable itself is going to be capital X.
Every time you put this one.
Yeah, it's not simultaneously taking all those values, it's just these are the values that it took. That's what consists of our data. Yeah, I was just trying to make it be familiar with, okay, if I represent a matrix, what does the column mean? The column is just the jth coordinate of all these observations. So maybe it's a measurement of just the temperature. All the different temperatures and different temperatures.
You didn't have a way to
that is metadata, right? Yeah, well, you're not using that. Yeah, this notation is just useful for subsequent tasks. But if you think of a label like temperature or something, you don't have to explicitly write it. I mean, it will be metadata, but it's not useful for our task or something, right? You can introduce such things as needed.
So if I say like X subscript J, will that mean
I haven't given a notation purposely because I've already used subscript I, little subscript I, and I want to use capital subscript I to represent the jth variable coordinate. So I still want to keep it a variable. I don't want to. So the matrix I have put a dash here. Yeah, you can just define that this with a dash and subscript J represents the jth. You can do
So how are you planning to go about this? each technique and then implementing it with cards?
No, it's gonna follow the statistical learning group. So you have access to syllabus?
No, I don't have any answer.
The syllabus is not related to Blackboard. It's just a public page. Just send me an email or something. I can just show you the syllabus. I can just show you the syllabus. Oh, I need to plug this back in. So this is the syllabus. So what the timeline is and what are the topics. R will not get too integrated into the lecture because I'm still working on it. But R will take a component of your homework.
So I'll try to get to all because I'll have access to the resources.
I need to add it to Blackboard, so send me an email.
Just to clear up the concept around the model of when can you erase while it's when you can't?
You can always do that. It's just I'm saying that sometimes you really want to interpret things, right? So you may make a wrong interpretation. You can always do that. You can do a lot of things. Yes, you should know that it's an incorrect thing to do. If you're trying to derive meaning out of it. Like for cat I assign a value of 1 and for no cat I assign a value of 0. That's fine. I have two values now. I can think of it as a regression problem and do a regression type of stuff. But originally it was a classification problem. Okay? I can do regression as in like fit a linear model or something like that that I've seen elsewhere. But you fit that, you should remember that it's actually, although it's fit and it's predicting something, it's actually predicting the numbers 0 and 1 which have no order relationship. So maybe if it's predicting 0.95, yeah, you can round it to 1 and say this is a classification prediction of 1. But linear regression will assume order relationships. So actually you have three things, three outputs, cat, no cat and dog. Cat, dog and no cats or dogs. If you give 1, 2 and 3 or let's say 3 numbers, then assume that 2 is in between 1 and 3.
Which is not the case.
Which is not the case. So maybe there are ways to get around it. You want to look at it.
Is there an example of when it is okay? Like
Yeah, in binary case it should be fine. Like if it's cat and no cat, it should be fine. As long as you remember that there is no relationship. But if three things, the moment you put something in between, it's not here. Errors are not seen. There will be something that should be off. Yeah. We are not trying to go into details of that today.
so but it will be discussed somewhere. When you can. I can just access
Who is teaching that? Okay. I did give a presentation I think last semester. I don't know this semester. I mean, we'll figure it out. So if she is scheduling outside speakers, maybe I'm not sure. Yeah. Okay. So now let's look at a couple of the supervised learners, the methods that will let us construct these functions which map inputs to outputs, okay? And now we're going to try to, look at them without the notion of statistics and probability, and then look at the same two learners with the notion of statistics and probability, okay? So that's the second section in the notes. Two learners. Yeah, I apologize for my bad handwriting. Sorry. So we'll look at, so what are the two learners? One of them you might have already seen, which is linear regression. And the second one you might have also seen, which is the K nearest neighbor, okay? So we're going to use the word model to represent this function that we learned. So when we have this function, a mapping, which is called a regression function, a classifier, we're going to just call it a model, as loosely, broadly speaking, okay? When I say a model, just think of a particular classifier or a particular regression function that you picked somehow, okay? So let's look at linear models first. So what is a linear model? So we're going to use the notation that we introduced just before, but now we'll put some hats. So a linear model just assumes that the output is related to the input in this manner. Okay. So beta hat is the parameter of this model. Okay. It just means that if I say I have model 1, you can say, okay, that model 1 maybe y hat is equal to x transpose beta hat 1, and if I have the second model 2, I can say it's y hat is equal to x transpose beta hat 2. Okay, that's all I mean. So that's what I mean by the statement beta parameterizes the function or the model. Okay. So these x's and y's are the same as before. So because they're capital letters, these are variables. Did somebody say something? Okay, these are capital letters, therefore these are variables. And I said that these can, for example, here in this case, x is a vector. Let's say it's p-dimensional. Then beta is also p-dimensional, right? This notation superscript t just represents the transpose operation. Okay. If x is p-dimensional and beta is also p-dimensional, then what is the dimension of y?
It's a scalar.
It's a scalar. So let's just expand it out so that everybody is clear. So I said we're gonna always think of vectors as column vectors. So when I put a transpose, think of it as a row vector, right? And I said I'm gonna use subscript. I guess I didn't say it before, but I guess I'm gonna use subscript. Okay, to represent the jth coordinate of this input variable. So these are all capital X's. Okay. So just in my notation, I'm going to use lowercase x's like this and capital X's like this. Although they may look small, it's comparable. So it's just like this, right? So it's beta hat f1. Okay, so you just multiply x1 with beta hat 1, or in this case, huh?
It might be mistaken with the notation on top of that because you have to fill in.
Yes. Let me.
I want to remove that one.
Yeah. Yeah, that was just to, okay, so let's say beta subscript I or j represents the jth coordinate of the parameter beta. Then this is just, let's say sum over I is equal, j is equal to 1 to p of xj times beta hat j. Okay, that's what this means. Okay, it's a scalar. Now, what if I say, what if I told you that y hat is actually also is actually k-dimensional. Yeah. What if I said y hat is k-dimensional? Then what is the dimensions of beta hat? Huh? What is it? So I guess I'm a little bit incorrect here because so it depends on how you so if I make y p-dimensional, I want to keep it as a column vector, then it's going to be, let's say y hat is p cross 1, you know, this notation you might have seen in linear algebra class. So then let me just see, x transpose beta hat is the same as beta hat transpose x, right? So let me, instead of that, put a bracket, which is because I want to figure out what the dimension of beta is, and then I'm going to, in fact, not even put transpose, so I'm going to put x there. So this quantity here, x is, I know is p cross 1 because it's a column vector, then I just need to make, y is k cross 1. I said y hat is k-dimensional, so this is k cross 1. So k cross p. So it depends on how you write this equation out. But all I'm saying is the output variable can be both scalar and vector, and if it's vector, then you have a lot more parameters describing your model. Okay. If it's y is a scalar, y hat is a scalar, then you just have p parameters. If y hat is a vector, you have k times p parameters in this linear model setting. Okay. So I hope everybody understands why it's called a linear model. Why is it a linear model? It's important.
It's the linear relation between the output and input is same.
We draw it off.
Okay.
You're mapping the line between the output and input.
So okay, let me ask a different question. Let's say y is equal to beta 1 x1 plus beta 2 x2. This is basically just p is equal to 2 from the previous case, and y is scalar. Let's say y hat is scalar. No, I'm just asking. So I'm just trying to differentiate between two different models. So let's say whether the second model is considered a linear model or not. Okay, which is x1 square plus beta hat 2. Let's say p to the power minus x2. Whatever. Is this a linear model or is this a non-linear model? Okay. So we can, I guess terminology that you might want to use is that linear in coefficients and linear model. If it's linear in coefficients, then you would include this one as well, right? Because it's linear in betas. Linear in the parameters, okay. Depends on how you look at the function. I mean, it's a function, the function is parameterized with beta, okay. So there should not be any confusion. So let's just think of these as linear models for us. Okay. Now, so we want to find, so we want to consider linear models, which means that we only want to figure out functions which map input variables to output variable, one-dimensional variable, which looks like this, which has a functional form which looks like this. Okay. So we know in order to pick there are many such functions, right? For every different value that I can ascribe to each of these two guys, I have a different function, right? So which function do I pick? For that, I want to kind of bring in the notion of an objective. And in linear regression, you've already seen this objective. It's just the least squares objective. So let's say we have the data. When I said data, it was lowercase x1s to xn's. And I don't think I wrote y1s to yn's. So if there are realized values of y's as well, output variables, then I would represent it as y1 to yn. Okay. And then the objective of, not of, but so the objective that we pick is defined as a sum over, let's say I is equal to 1 to n of yi minus xi transpose theta square. This is the least squares objective that you might have come across, right? If you plug in different betas, you'll have different numbers like this that you can compute. For every beta, you can compute this number, right? You just take the ith observation, compute the inner product of beta with xi, subtract it from yi, get some number, sum such numbers for all the n different observations. You'll get finally one number, right? It's a scalar. You get a scalar. But for a given beta, you get a scalar. Right? So just find the best beta, and that beta is what I'm going to again represent as beta hat. Okay, and it is going to be best with respect to this objective. It's the one which minimizes this objective. Okay, the difference between the realized outputs and the realized inputs transformed in this way according to this linear relationship. Beta hat is going to minimize that objective. Okay, minimize as in this, it has the lowest scalar score associated with it compared to any other beta that you can pick to plug into that objective. Is that clear? Okay. Actually, potentially from your previous classes, so you might have seen the vector representation of this objective. Okay. So let me use y, which is n cross 1. Okay. Minus x. What was x before? N cross p, right? Sorry, not x. This is n cross p times that beta, which is p cross 1, right? I'll try it this way. So this is the difference between two n-dimensional vectors. Okay, where this capital Y with a small bar towards the top right just means that it's the concatenation of the realized values of the Y output variable. So output is scalar, okay, because our model has p parameters, okay, p degrees of freedom. So this is just a difference of two n-dimensional vectors, right? I just wrote. So this is nothing but I just wrote it this way, right? I just wrote yi minus xi transpose beta. Yeah, I just stack them up as rows. Okay, if you look at each term in my objective, I just stack them up as rows, and since I want to square them, I just take whole transpose of the same thing, y minus x beta. Okay, so this is just going to give you the same objective that we saw a couple of lines earlier. Should write it more cleanly. We can actually quickly derive out the optimal. So what is the best beta here? Okay, if that was the objective. So as I said, this is nothing but this is the same as sum over I is equal to 1 to n of yi minus xi transpose beta. Right? This is the same thing in the vector notation. Okay. Do you guys? Sorry. Do you guys agree that the this term is a scalar? See, this is an n cross 1 vector inside. I'm taking a transpose, so it's a 1 cross n vector. And this term here is the same as this, so it's an n cross 1 vector. So it's an inner product, which you should be familiar with, inner product of two vectors, the same dimension, and so it's going to be scalar. Okay. Now, so I want to illustrate this because I want you to be familiar with matrix algebra, because it's a prerequisite for this. I mean, you need to have a familiarity with matrix algebra to kind of be in a comfortable position in this course. So let's actually get the I think from calculus class you probably remember that if you want to maximize or minimize some function, then you set the derivative equal to 0, right? So here we're going to set the derivative of this objective with respect to beta equal to 0 and see what is the best beta that we get. Okay. So you can see that this objective is quadratic in beta, or each coordinate of beta. There are p free variables, or p variables that you want to figure out. Okay, it's quadratic in that. Now let's set the derivative equal to 0, but instead of doing that for this doing it for this form here, we're going to do it for this matrix version. Okay, so let's actually do that. So this is just y transpose minus x beta okay transpose times y minus this is the objective. How did I multiply? I just expanded the brackets, right? Now so bad thing that I'm at the end of the page. Okay, I'll just okay, so anyway, this is the objective. So you can see that it is a quadratic because so first of all, each term is going to be a scalar. Okay, if you just match the dimensions, for example, y transpose y is just 1 times 1 cross n is this is just an inner product of two vectors. Okay, it's going to be a scalar. Similarly, this is also going to be a scalar. In fact, I'm just saying that all these are scalars. Okay, we're not dealing with, it's just a function of beta, which is actually a vector, but it's a scalar function. Okay, yeah.
Sorry for a silly question. What is scalars?
A scalar is just a one-dimensional number. It's like a number, a real number.
Okay.
Yeah. A scalar is just like a value 1 or 2. Yeah. A vector is just a concatenation of scalars. Yeah. Okay, so let's take the so these are linear functions of beta, and this is a quadratic function of beta. Okay, because if you see beta is getting multiplied with beta, so there will be terms like beta square, beta I square, beta I, beta j, and so on. Okay. If you okay, thing is I'll lose this, but it's okay. Let's actually directly write the expression for the optimal solution. I wanted to do the derivative, but I think for the first class let's not do matrix derivatives, but I would suggest if you have time, look at matrix derivatives. Like for example, if you have ax and we want to do d by dx of ax. So here A is a matrix, okay? I'm just going to give you a hint basically. A is a matrix, let's say it's P cross P. Just for example, let's say x is P cross 1. Okay, x is a vector now. It's not a scalar derivative that we're taking. So this derivative is what is this derivative? For linear transformation. Okay, let me know. So actually, your function is not scalar, so let me make it a little a. Yeah, I'm just showing derivatives in a vector notation. Okay, this you can actually expand out the objective and do your calculus on each term, each scalar term. But let's say A is a P cross 1 vector as well, and my objective is A transpose X. Okay, I've written my objective in terms of a vector, right? It's a scalar because A transpose X is an inner product of two vectors. It's kind of a scalar or a single number. If I take the derivative with respect to X, it's just okay. This is a vector, it's P cross 1. So actually, we can just see that, right? I mean, if you wanna, this is just a hint to figure out the least squares beta hat, but we'll see what it is. So this you can actually just easily see. This is just sum over, let's say I is equal to 1 to P of AI times xi, right? This inner product is just written expanded it out here. If you take the derivative with respect to each, let's say xj, let's say fix j, fix j to be equal to 1. Let's find this out. This is going to be all the other terms which don't involve j will go away. It's going to be just aj, right? So you do this for j is equal to 2. You get I guess a1, a2, and so on. And so that shorthand notation here is that you're doing all the derivatives with respect to the vector x, and you're getting a vector which is a concatenation of all these guys. Okay, that's just one example of a vector derivative. And similarly, in the previous, for example, this term is an inner product of two vectors, beta and something else. Okay, the something else is x transpose y, but you can ignore. You can just think of this whole thing, capital X transpose as a matrix x transpose vector y as sum A. Okay, because it's not a free variable. Then you have a beta transpose A. Its derivative with respect to beta is going to be just that thing that is getting multiplied. Okay. Anyway, so this is just to illustrate that you can find the optimal or the best beta hat. And just, if you remember the formula from your stats class, it's just going to be x transpose x inverse x transpose y. Okay. This is just the least squares solution, which is that particular P cross 1 parameter that minimizes that objective, which was I is equal to 1 to n of yi minus xi transpose beta square. Okay. Anyway, and we don't really care about the particular expression. I'm just saying that at least a least squares objective, and if you want to look at linear models, you have a closed form. This is called a closed form expression because given your data, which we arrange in the matrix and the vector form, you can just get what is the best parameter which kind of reduces this. Okay. Why do you reduce this? Because remember, we wanted to somehow come up with a function. In this case, we're getting linear functions. Function of any new input variable x, which is somewhat close to the true value that it takes. Okay. We want to predict that. So in the notes, I have a two-dimensional example of data. Okay, so let me describe what the data is. I'm gonna draw a quick plot here, which is just a replica of what's in the nodes. So think of 2 dimensions, x1 and x2. Okay, have a bunch of points here. And I've also drawn a line in the nodes if you see. Okay. So let's focus on the scatter plot. This is called a scatter plot if you ignore the line there. Okay, it's just a plot of 2 coordinates of your input variable. Okay, the observations. For example, this x may represent a particular value that capital X1 takes and a particular value that capital X2 takes. Maybe it's the first observation in your data. Okay. So you have this data, and if you so the x's just represent. Okay, in this example. Okay, in this example, it happens that we actually have qualitative output variable. So we have a g, okay, which here takes I don't know what colors these are. I think orange and blue, right? G takes two I guess symbols or semantic values, which are orange and blue, and so in this scatter plot you can always color the point to be orange or blue, just representing what its label or what its label is basically. Okay. In the first part of the class I said, okay, can we just use y instead, and we can use y instead of using the we can say orange is 1 and blue is 0, and then we have a quantitative number now, which is either 1 or 0, and then we can just use linear regression. Okay. So we can use linear regression. So therefore we can get we can arrange all these points in the scatter plot as the x matrix. We can arrange all the y's as the y vector, where maybe for orange it takes 0 value and for maybe blue it takes 1 value. Okay, we have these two from which we can get that beta hat, right? So you can just apply the previous bunch of matrix vector products. So do all of you know what a matrix inverse is? If you see, I think in the previous equation I put a -1 here. Actually it's not very clear, but that's -1. Okay. So inverting a matrix is something you might have seen in the linear algebra class. It's kind of, you need to be familiar with these topics. Okay, somehow we got the beta hat. Now let's ignore the current points, the x's and the dots. Okay, let's redraw the whole thing again. Let's redraw the axis and let me put squares. Okay, I'm gonna put squares at evenly spaced locations. Another way, squares everywhere basically. Okay. The reason I did that was now I'm gonna use beta hat to make I can compute y hat, which was basically what x transpose beta hat, right? That was the linear relationship. So once I have figured out the model using the data, which is this underlying thing, I can use the beta hat below and make a prediction. Compute possible output value. Okay, at every location in the 2D space. Okay. So this is the 2D space. It's just a plane, right? So for example, here I can just compute what y hat says, okay? Because x is 2 dimension here, get the 2 values here, maybe x is something here, x2 is something there. So plug those two in, you have the beta hat, get a number, okay? And for convenience, I'm gonna actually transform the y hat to an estimate on the qualitative value itself, which is going to be, I'm going to use the notation 1 bracket y hat greater than 0.5. Okay. So So what is y hat? Y hat is just a scalar, as in it's a number. Okay, it's going to be a number. I'm going to say if the number is greater than 0.5, I'm going to assign the value 1. Okay. So g takes the value 1 if g hat takes the value 1 if y hat is greater than 0.5 and 0 otherwise. Yeah, if the other definition holds. Okay. So I somehow converted these y hats. I was doing linear regression, so I was actually getting y's which were continuous, right? I mean, they don't have discrete values. I just converted them to discrete values by using like some sort of what is called a threshold. So any value which is greater than 0.5, let me push it to 1. Any value which is less than 0.5, I just push it to 0, and so I get back 1s and 0s, and so it's close to kind of the blues and oranges that I need. So if it's 1, like maybe I'll just color it as orange, and if it's blue, I'll color it as blue. So that's how you get the in the notes. That's how you get the colors on the two sides. Okay, and there will be a boundary where on one side you'll have one color and on the other side you'll have another color. Okay, that is called a decision boundary. Okay, and that decision boundary is this straight line in this 2D case. Okay, so maybe above this it's orange, and maybe below this it's blue. Okay. So the reason I drew another plot and kind of removed the x's and the zeros, which are our data, right? Is to just show that to show where we are predicting or suggesting it should be orange, and where we are predicting it should be blue. So, for example, given the data, we somehow got beta hat. Now we can completely ignore the data, right? I mean, from data we somehow constructed this beta hat, which is our regression function, or regression function's parameter, right? Now given the beta hat, give me any new point. So that's why I said, okay, let's look at any point in the space. So that's why I evenly space the points, just to kind of tell you that I can pick any point in the space. Okay, let's pick this point, multiply that point with beta, and I'll get a number. I'll look at the number whether it's high or low, and I'll assign that point to be either blue or orange. Okay, and I have a decision boundary which happens to be linear, and it's linear because we are using a linear model. Okay. Any questions? Yeah.
What do you decide the threshold?
It was arbitrarily decided here. We will actually see the nuances of deciding the threshold. So a lot of things are, I'm just making a choice, and I'm making a choice that I'm going to use a linear model. I'm making a choice that I'm going to decide a threshold of 0.5. We'll see how those choices influence whatever we want to achieve. Maybe forecasts, which go into decisions, and so on. They all influence these things later on. We will see how these choices influence throughout the course, actually. For now, since we have not even introduced the vocabulary of statistics and probability here, I didn't say anything about randomness or anything. So for now, just think of it as some choice I took. Okay. Any other question? Yeah.
So you randomly select some point from the second graph and you correct calculate the beta hat.
No, second graph is just an illustration. You can kind of ignore the second graph if you want. From the first graph is just to illustrate how my two-dimensional data looks like. So since my data is two-dimensional, I could plot it on the plane, and since I have this color, which is the output variable, realization's output variable, I just put x's for orange and zeros for blue on this thing. I mean, on the notes you have probably all zeros, but they have colors, so I couldn't write colors here. I can actually do colors, but anyway. So that's the first plot. That's my data. From the data, I just use the previous formula to get this beta hat. So this formula, the arrow, to get the beta hat. And once I get the beta hat, all I'm saying is I can make basically a prediction or an estimate of what the output should be at any given point in the space. So I just said, okay, to kind of give an idea of any given point in the space, I just said, okay, let me think of all these evenly spaced points in the space. I can always color them, right? I can color any point in the space. I didn't have to draw this plot, but I just after I have beta hat. Yeah, once I have beta hat, I can ignore my data. You don't want to use random there. I mean, you can apply beta hat to any point in your space. Like you don't have to look at this particular plot, right? Actually, plot is not even useful. You can pick any point. Don't use the word random because it's a little loose. But pick any point and you can color it. Okay, according to this threshold that we chose. The decision boundary is actually, is nicely given. In fact, what happened to? Sorry, I'm just trying to figure out, did I lose something? Okay, that's fine, I guess. Huh? Control C. Edit, undo. Yeah, undo. Okay, awesome. Yeah, so how did I get the decision boundary? That's because if you look at it, I'm trying to color the points orange if I have x transpose beta hat greater than 0.5, right? And I'm going to color things as blue if I have x transpose beta hat less than equal to 0.5, right? So the boundary is just x transpose beta hat is equal to 0.5. I mean, so intuitively you can see, right? If I color orange on one side, I color blue on the other side, I guess. Let's say, what did I say orange was? It's above, but did I say anything about orange being 0 or orange being 1? So let's fix orange being 0, okay? Then, if x transpose beta hat is less than 0.5, let's say we classify it as orange, okay? Because x transpose beta hat is the value that y takes, and if y is closer to 0, we'll just push it to 0. And so since 0 represents orange, as long as this condition holds, we're going to color that x orange, right? But when does the condition stop, when does the condition start violating, as in doesn't hold? It doesn't hold when, okay, I guess I should not put equal to, I think you can put equal to, but when does the condition not hold? When x transpose beta is exactly 0.5, then it's no more orange. But the moment x transpose beta hat is beta hat is greater than 0.5, I said I'm going to map it to ones, and the ones represent blues, so that is blue. So only place where the place where I transition from orange to blue is exactly when at this kind of critical boundary. Okay, slightly above that is orange, slightly below that, slightly below that is orange, and slightly above that is blue. Okay, that's how you get the decision boundary, and you can see that this is a linear function in X. Okay. Yeah.
One is that if we have such a distinct decision function, how are still the red and orange are meshed up into each other?
That's the training data. That's the data that we had. So in the data, we had that some of the points had, somebody told me that this point has a blue or this point has an orange. It just so happens that from assuming a linear model and creating this decision boundary, I'm not able to ensure that all the, in my data which points were orange but actually, are also orange, and the points which are blue are also blue. So things are more, mixed up. Yeah. That actually brings to the limitation of linear modeling, that it may be you're making this linear assumption, so it may be too strong. Okay.
And the second thing that if you have made a decision point of 0.5 which is static, so should it be basically as a horizontal?
No, it may not be horizontal.
You prefer a stationary or constant, right? So constant is always.
Yeah, so let's ignore all this data stuff and let's look at two things. You've seen y is equal to, let's have two coordinates, some x-axis and some y-axis. Okay. Can anyone tell me what is the equation for this line. Okay, let's say y is equal to x, or let's say in general is y is equal to some alpha x or something, some with a different slope, okay, potentially. Now, this can be also written as y minus alpha x is equal to 0, right? What if I draw a line like this, okay? We don't have to actually, exactly figure it out, but all I'm saying is you may have some alpha x plus beta y is equal to some constant or something, okay? This x transpose beta is like the x and y's here. So this is like x1 beta 1 plus x2 beta 2 is equal to constant. That's all it is, okay? If you're not following, just let me know. It again. Yeah, so why the addition boundary is linear is what I was explaining. It just happens to be linear because the function itself is linear. X transpose beta we have assumed to be linear, and we're just asking when does the function take a value which is constant. Because the function itself is linear, it will take, it's basically, it looks like a line in 2D, and if you can imagine in 3D it's going to look like a plane, okay? In higher dimension it's going to look like a hyperplane or something like that. Anyway, it's just linear, linear just means like really like a line. So that's linear modeling. I mean, in the sense of assuming a linear model and maximizing a certain objective, which was this error, square error between the realizations of the output minus the linear model assumption with the realized values of the input. Okay. For that objective, we got beta hat, and we saw this is a line, and it's not really pushing even my data, for data for which I know that something is orange and something is blue, it's not pushing the oranges to the one side and blues to the other. Okay, that's what we want to create a classifier here actually, but we transform it to a regression problem, and we were, it's a little bit unsatisfactory. So you can imagine that there are some problems where you cannot really push the oranges to the top and blues to the bottom in the 2D graph. For example, let's say my data was actually generated from a two-dimensional Gaussian. Okay, does everybody remember what a Gaussian distribution looks like? In one dimension it looks like this. Probably it doesn't go to 0 actually. With some mean, okay, and in 2 dimensions you can look at what is called a contour plot. So you can look at it from the top, and let's say it's a spherical Gaussian. It just means that the variance in each of the 2 directions is the same. Let's say it's 1, okay. You can look at the top view, and it looks like something like this. Okay, it's basically a high value of the mean and kind of decaying as a function as you go outward. Okay. The reason why I brought up Gaussian is because let's say our data was actually from Gaussians. Let's say the orange points were actually just we sample a point from this 2-dimensional Gaussian. Okay. Maybe we got data from this 2-dimensional Gaussian, which is these oranges. Maybe it need not be symmetric or any, need not be spherical or whatever. Maybe from the blues you got from some other Gaussian. Okay. For this, you will see that you may get a point here which is blue, and you may get a point here which is you may get a point here which is blue, which is the circles. You may get a point here which is orange, which are the x's in my notes, right here on this blackboard. And I got a line which is a decision boundary, which is saying this is the top side is the orange, the bottom side is blue. You can see that there will always be points which I cannot figure out whether they are blue or orange using my beta hat. Okay, because just for chance I may get a point which is this circle here, which is on the other side of the decision boundary, and my beta hat by thresholding will always say that it's orange. Okay, so it will always have some error. Okay. A Gaussian distribution is the same as a normal distribution. Yes. Yeah, I didn't want to introduce the notation and all that. It's just because there is a particular density function for Gaussian, but we don't care. I just want to illustrate that if the data was even from a nice Gaussian, the orange is from a nice Gaussian, and the blues are from nice Gaussian. If the Gaussians are like far away, let's say, okay, then maybe a line like this will almost, do a good job, pretty much almost no error. I say almost because Gaussians actually have the support of the distribution is, for example, for one-dimensional Gaussian is from -infinity to infinity. So you can always realize a very large value, or you can always realize orange which is over here, but it's very, very unlikely. Okay. So for that example, so I guess coming back to that particular two-dimensional example, linear model doesn't seem to be doing well. So let's look at a different model, which is called the nearest neighbor method. Okay, I guess the method nearest neighbor will give you a model of will give you a function to assign these colors to again new points. Okay.
Professor, just before you go to nearest neighbor, you explain why again linear model is failing in this case?
It's not failing, it's giving me something. I'm just saying that okay, so let me try to answer it properly. So it's not really failing, right? By looking at this plot, some people may be happy that yes, it is classifying majority of oranges correctly and majority of blues incorrectly, right? I guess you are not satisfied that it is putting some blues on the side where there are some oranges and so on, right? So that's what we are not satisfied with. So that stems from, and in fact this whole lecture is about that, is that you don't know how the data was generated. The whole field of statistical modeling is that you've been given data, you don't know how it was generated, okay? And you want to compute something from that, like a classifier or a regression function that you want to use for some subsequent task, like forecasting, which will maybe lead to decisions, right? As we saw in the car racing example. So we don't know how the data was generated. So here I was just illustrating that even if the data was generated using Gaussians, it just happens that the Gaussians are overlapping too much, then the linear model will not be able to separate the two, kind of put a boundary between them so that you can do better than this. Okay. So let's say in the 2D example, let's say the data was generated from this type of two Gaussians. You can actually show, like some theoreticians have shown, that this is the best thing you can do. You cannot have any other classifier or any other function, a mapping, which can map things to orange and blue better than what a linear model is doing. Okay, better than this actually. So in the sense, you will not be able to get better errors. Do better in terms of the error value, like things which are on the wrong side of the boundary. Okay.
I mean, 1D it works perfectly.
No, even in 1D it's the same thing. I mean, we just pick 2D as a case. So let's look at 1D. So let's say in one dimension, it just happens that you have two Gaussians, which are like this. So let's say this is orange, and this is blue. Okay, and there's only x1, so you only have to find beta hat, which is actually just a scalar. A scalar just means, as I said, one-dimensional thing. So here, in fact, if you have enough number of training data, which is at n, if you have, we have n observations, right? If you have a decent number of them, let's say, then your beta hat will be almost over here. Beta is just a scalar. It's like again I lost stuff. Damn. No. Okay. Beta is just a scalar, so you can think of it as like a point here. So anything on the left side is classified as orange, anything on the right side is classified as blue. Okay. So even here you can have a blue which is I guess circle. Yeah, blue is classified as orange, and so you can't distinguish between this circle and maybe an X. Okay. So these are distributions, by the way. You'll get samples, but those samples are all going to be on the x-axis, so you will not see this distribution. If you draw a histogram, maybe you will see like a Gaussian curve, but this is just showing that the two distributions overlap, so you can't really figure out if you get something from here with high probability, according to the Gaussian, it's an orange, and with some low probability, it's actually a blue, but you'll not be able to distinguish. So this actually alludes to, yeah.
Can we add any array function to represent this topological area?
Array function. So we haven't even got into the language of statistics yet. We'll get to that in the next section. But see, even if you somehow want to kind of represent this error and try to minimize it, so we need a representation, right? Just like we have representation for input, output function, we need a representation for what it means to be an error situation like this, and then maybe you can minimize it. And I think it's probably related to type 1, type 2 errors. Like all I'm saying is, if you can represent this error, you may be able to minimize it at the expense of something else potentially. But it's possible it will not go that trajectory at all today. Okay, or even today. I just wanted to say that, okay, if you have a bunch of points, fit a linear model, even if it's a classification problem with just two classes, or whatever, not two classes but two values, orange and blues, you can use linear regression, you'll get some answer. It may or may not be satisfactory, but it all depends on data. Okay. So that's why we want to switch to another method. It's a very different style of method, so it's kind of contrasting from this linear regression model, which is as follows. So it actually doesn't even estimate any parameter beta. Okay, it's a very intuitive method, but actually you should probably try for, if you get data, you should probably always try that first, which is this nearest neighbor method. And all it says is, okay, you've given me data, okay, yi comma xi, I is equal to 1 to n of these pairs of, realized values. I'm gonna, so let's say you give me a new x, okay, and you're asking me what color, let's say in the 2D case, what color does, at this x point, little x, what color should I assign, right? So this particular method has a parameter which is k. Okay, I'm going to say what k is. It's again a scalar. It's one number which parameterizes this method. And y hat is just going to be one by k. It's actually little k. Sum over all the xi's which belong to the neighborhood of x and their y values. Okay, so I think it's easy to kind of understand this graphically. So let me just space. I was saying is we have a bunch of these 2D points. Or the x is above. I think so. Okay, let's see. So all these bunch of points. Again, to the example. Let's say I want to find, this is my x. Okay. I'm asking, can you tell me what the color? What is the color for this particular point? You can just consider neighbors of this particular point x. It looks like the closest points are this one and this one. Okay, looks like from a Euclidean distance perspective. In the sense, pictorially, it looks like these two are the closest points. These two take color blue, so let me just call the color of this guy to be blue. Okay, that's what the nearest neighbor method says. Okay, the k just is a parameter which just says look at the k nearest neighbors. Okay, so in this case it's a 2 near neighbor method. Okay, so if I pick a point, for example here, maybe look at these two guys and assign orange there. Okay. Yeah.
So in the case of two near neighbor, if you have like one blue and one orange, then you should just randomly assign.
Yes. Yeah, that could be ambiguity, which I don't think that referred in the notes. Yeah, you probably have to randomly assign. Yeah.
Would you just pick the cluster of the two? If one was still closer than the other, if you have two neighbors and the green is still closer than the orange, you would still choose green.
Yeah, but you will need to do some some clustering, right? So you need to have some. So here we just have gotten these observations, these realized values of x's and y's, and from that directly we are applying this k nearest neighbor. So we don't have any notion of clustering here, right? Because we just got this data and we're just applying KNN, 2NN method, for example. If you did some clustering, you may have additional information and you can probably post-process in some way. But here, it's not the case.
How do we decide the value of k?
Yeah, so we're going to discuss that. Yeah. Yeah, actually, interesting point. I don't know if it comes here. Okay, so how do we decide k? That's a very good question, because that's the only thing that I think it looks like we can control, right? So let's pick k is equal to. So here in this example, I took k is equal to 2. So what happens if k is equal to 1?
All will be 1 plus c.
It will only look at one nearest guy, right? Maybe one of these two x's is the nearest, then maybe it will just take that. Okay. Now, if we do k is equal to 1, how does the decision boundary look like? So, okay, so I guess the more general question is, the simpler question is, how does the decision boundary even look like for this method? Right? Just like linear regression, it is a line which cut in the 2D plane. For this method, it happens that I think, so the figure 5 in the notes is showing the 15 nearest neighbor method. So it's taking the 15 nearest points and taking the, getting a value and assigning blue or orange. So there, it looks like the decision boundary is highly wiggly. Okay, it's not linear anymore, it's just all over the place. If you take k is equal to 1, I don't know if you have, yeah, I have the picture. So if k is equal to 1, you will get a lot of, so you'll get again decision boundaries, which are represented as black lines. They are more irregular than the 15 neighbor method. Okay. So I don't know if I can draw this. So for example, if k is equal to 15, it looks like this. Okay, here it's all oranges and it's blues here, majority, I guess, a lot of it. Maybe there's some blue here, maybe there's some orange here. Right? It still doesn't put all the blues in the same side and all the oranges on the same side of the decision boundary. But for k is equal to 1, it will actually do that. Okay, why do you think it is? It will put all the blues on the same side and all the oranges on the same side when k is equal to 1.
We can't try a proper regression line.
There is no regression here. This is just using one parameter k. I took k is equal to 15. It took some blues on one side, some blues on the some oranges on the one side, but some blues and oranges were on the opposite side of the decision boundary. It seemed like a single decision boundary. For k is equal to 1, you don't have to have a single decision boundary, right? You can always say in the 2D plane, maybe I have some oranges here, some blues around it, and maybe again oranges here, some blues around it. Maybe this is a decision boundary. I mean, it doesn't have to be so nice, but you can see that there could be some parts where there is orange, some parts where there is blue. Okay. For k is equal to 1, Okay, I'll tell you what's happening. So for k is equal to 1, it's going to put all the oranges on the same side as orange. It's going to forecast that, okay, it's going to make predictions, right? And you can always plug in the data that you already have and see that the data that you already have is always on the right side of the decision boundary. In the sense, if your observation xi, yi, or actually in this case yi, which is transformed from this gi, let's say gi is orange, okay? If gi is orange, then yi is some value less than 0.5, let's say. It will ensure that orange is in your training data, in your data that you've been given, is always on the orange side of the decision boundary. And the decision boundary need not be one single line. It can be like this is a boundary here, this is a boundary here, this is a boundary here. And in figure 6, there seems to be a more wiggly version of the same thing that I've drawn here. That's because you're using the data that you've already seen. In a sense, the data that is describing your nearest neighbor method is being used to evaluate your nearest neighbor method. So for k equal to 1, you'll get all your answers correct because we're asking for the right answers. We're asking for the answers on the data that you're using. Okay? It's related to something called in-sample testing. So you fit a curve. In this case, if you have we have outputs, inputs and outputs, we're fitting a function, getting a function from there, which hopefully makes good predictions, but you evaluate the function on the data that you already have. Okay? It's called in-sample evaluation. Okay? If you do that in-sample evaluation for the k nearest neighbor method for k is equal to 1, you'll get a array of 0. Okay? Which doesn't mean anything. Okay?
What happens if we select data one that is exactly equivalent from blue and like on the boundary of the both blue and orange?
So what is the boundary? So the method is giving you the boundary. So we're saying in the ground truth there is some boundary where data point can go blue and orange with some with something.
From both, I mean we have a data set like the training data set and now we are figuring out the point and we should be assigning. And it will be listened from both the blue and the orange point.
Yeah. Then it points to the same question the other student asked. You probably have to flip the coin and assign it something. Yeah, assign it something. That's a good question. It's a good question in the sense, does it happen often in your data or is it once in a million case? Once in a million case, maybe it's okay to give up on that part. But if it's too often, then you want to consider better modeling. So that is where. So this course is about where will things fail and why are they failing. And we look at linear regression. It seems to be fine, but it's not doing a good satisfactory job. So we switched the method to k nearest neighbor, and it seems to be doing fine. At least for k is equal to 15, the k is equal to 1, we realize that we're actually testing it. We're actually evaluating how good we're doing on the points that we already know the answer for, or the points with which he used to build the classifier in this case. So those were the two methods that we saw for this same data set. Of course, we don't know what they generated the data. We have not revealed. Actually, in the book, they reveal how they generated the data. But it's intuitive that if you had a mixture of Gaussians, like not mixture of Gaussians, but if you had two Gaussians, the picture that I draw before, then it's intuitive that maybe just going with the real model is fine. Okay, but if you have like several Gaussians and some of the Gaussians are blue and some of the Gaussians are orange, then maybe you need a non-linear boundary, and so maybe you should go with k nearest neighbor. So that's just intuition right now. Okay, we haven't even introduced the notion of statistics, which we'll do a little bit in this class and we'll get in the next class. Okay, we just so today I think we just introduced ourselves to both these two methods. Okay, for the two-dimensional case. So one last thing that I wanted to quickly go through is comparing, so I just pointed out the flaw that we were in our thinking, which was we were just evaluating it on our training data. That doesn't make sense. When k is equal to 1, you can put all your training data exactly in the orange or the blue decision regions, characterized by the decision boundary correctly. So you'll have an error of 0. So you need a notion of testing. Okay, you must have come across this in stats class where not hypothesis testing but testing. So if you do linear regression and you fit a model, you want to have some other data where you see how your linear regression model is performing, right? So the same notion is being, I guess, generalized to all supervised learning tasks. So any regression doesn't have to be linear regression. Any regression or classification task, you need to probably do testing, as in you need to have some other data where you evaluate whatever model that you build, whether it's a linear model or a KNN method-based classifier. Okay. So I'm just going to replicate the plot that we have in the notes. I think figure 7. It draws n by k on the x-axis. Okay. They could have just chosen k, but let's say it shows n by k. And here they show test error. Okay. So what is test error? It's going to be just the same thing. Let's say I have some y tilde I and x tilde I is equal to 1 to n. Let's say I'm just introducing notation, but all it's saying is I have data which was yi and xi, which were n in number, right? I is 1 to n. Instead of that, I have y tilde I, x tilde I, which is something different, which I'll call a test data. And I'm just going to look at what is the value of some error I is equal to 1 to n of y tilde I minus this function, the classifier, which could be a linear classifier or the KNN method. What does the function do on x tilde I square, let's say. This is my, it's the same as the least squares array, except that I'm using different data points now. Okay. So for every x tilde I, you can do the KNN evaluation and figure out what the color of that. And in this case, you don't need colors. You can just stay in the domain of y's, if you want to. You can replace y's with g's if you want. It's okay. So that's the test error. And you can see as a function of n by k, there are two curves here. There's one curve which seems to be hitting 0 at some point. It so happens that this n they chose to be 200, okay, in this two-dimensional example, and it's going to hit 0 when k is equal to 1. So at the point 200 on the x-axis. If you look at the, it's not really at 200, but very close to 200. So this is actually the training error, or the in-sample error. Actually, to expand it out, it's just y equal to 1 to n of y minus x f of xi square, let's say. Okay, it goes to 0, but so what's happening? So towards the right, k is smaller. Towards the left, k is larger. Okay, because let's fix n. Okay, it's just a constant. N is 200 pounds. I've been given 200 pounds of data. I should not do anything. I'm not going to change it. I change k, and k is larger. I'm going to be on this side. When k is smaller, I'm going to be on this side. You agree? Because it's 1 by k basically. So when k is larger, I have a 1 by k, which is a smaller number. So I'll be towards the left side of this plot. Now, towards the left side, it looks like the error, the training error, is pretty high. Okay. So that's the training error. That's at different points I can just evaluate for different values of k. I don't know how to fix k. So for every k, I'm just computing this number and I'm plotting this curve. Okay. Actually, there's no line. There's just these x's. Because maybe here k is 1, maybe here k is 2, here k is 3, and so on. Right. Now there's this test error that I can also compute. which it looks like it's going down, and then again it's going up. Some U-shaped thing. Okay. So it looks like when you actually pick K to be really small, you will have almost zero error for the data points that you have used to actually build your KNN classifier, but your test error is really high. Okay, that the decision boundaries. So basically, the output of a classifier, one way to visualize it is just the decision boundaries. The decision boundaries that you get for K is equal to 1, they seem to be so correct for your data you have that will be completely off for the actual test data. So let's say the data was not. There's basically one loose word that I'll use is basically overfit somehow. Okay, we'll actually kind of understand what overfit is again now in terms of properly next time. So maybe a sweet spot is this K, some K over here, but clearly you don't have maybe you don't have lots of test data, maybe you have limited test data, you will probably not know which is the right K. Okay, that's another shortcoming, and that's the shortcoming for any model. Here they have also plotted linear model, how it does for P equal to 3. So they took not P is equal to 3, sorry. P is equal to 3 because it's a two-dimensional data with one intercept. So if you think of a linear model, it's like not just beta 1 x1 plus beta 2 x2, but there will also be a plus c over there, just to ensure that the linear model is not going through 0 all the time. So anyway, so that's the performance of these two methods for this two-dimensional data. Okay. So this trend of test error increasing as training error goes to 0 is something that you should watch out for. So you may do really well in your particular application for the data that you have collected. You're managing gives you data, you're doing really well. But if you deploy it in production, like in the sports analytics case, if I actually have forecast this decision aid tool and says pick every lap, so that's a really bad decision. But that's probably because the model was overfit to the training data like anything. Okay, so we'll actually discuss this particular plot again. We'll come across this plot to understand how test error and training error vary. So throughout today's class, I did not even say that X was a random variable, but in the next class we're going to now add to our vocabulary the statistics or the probability aspect of this problem, and then we'll have so what will happen is the first couple of lectures will just introduce the vocabulary, and with that same vocabulary you can look at KNN methods, you can look at linear methods, you can look at all other methods that you've probably seen in your other classes or other projects. Okay, so that's it for today's class. If you have any questions, please ask here or after the class. Yeah. Oh, it just shows that it's like a majority, right? I mean, I'm taking 15 points. I want at least 8 points to say orange or blue, and whichever is higher, I'm just going to say orange or blue. So it's just like the same thing as 0.5 for each one. Half the points have to be one color. Sorry. Okay, so lab sessions are going to be from September 9th. Yeah. So September 9th will be the first assignment will also be out. So lab sessions will start that day.